Good evening, and welcome to the week 4 of the live interactive session of the Fabrication Techniques for MEMS-based Sensors, a Clinical Perspective. I am the PMRF Teaching Assistant of the course, Vikas Pandey, from IIT Jodhpur. So this is a brief about me, and you can see more details uh, on my portfolio. And this is the Meet link we use to connect, and all the recording of the classes will be available here on this YouTube channel. And if you want to reach me, you can write to the email mentioned here. So let's discuss some questions related to this week contents. The first question is, we can improve the sensitivity of the sensor by using nanostructures of a metal oxide than using a normal metal oxide. Is this statement true or false? So here uh, we are talking about nanostructure of a metal oxide and a normal metal oxide. So it is like remember we talked about ID pattern. So let's suppose there is an ID pattern, and on top of it, since we discussed earlier also that there will be no conductivity, so the resistance will be infinite. Ideally, the current should be zero when there is nothing on it. But when we put something, like suppose we are putting suppose here we are putting some material, and in this case it is a metal oxide. Metal oxide. So if we are putting a metal oxide here, which is a non-metal oxide, there will be some conductivity due to the property of the metal oxide that it is a bit semiconducting in nature. Whereas, if instead of this metal oxide, what we do is that we create nanostructures, that is nanorod, nanoseed, nanorod, or other nanostructure of this, and then we deposit it over it instead of this. So it says that it will be more sensitive compared to a normal metal oxide deposition. Is it true or false? So to to understand it, let's first see how what is the difference between a normal material and a nanomaterial. So as discussed in the class also, they are in the range of these are nanomaterials, nanotube, graph, graphene, single layered material. So they have structures uh, in the range of nanometers, and such small since they are having at least one dimension in nanometers, they have very high surface area to volume ratio. That means there are many more sites compared to a bulk material. There are many more sites available for the molecular interaction to happen. Like this, I have taken one. This is an image from some people. So these are ZNO, zinc oxide, nanomaterials, like different kind of rod kind of structure, flower kind of structure, some chip kind of structure. And in all this, you see that these have very good surface area, and as such, more molecules can more molecules of the more biomolecules or gas molecules or whatever sensor we are trying to make will be able to interact on these sites, and as such, the overall sensitivity will increase. That is why we can say that this statement is true, that having nanostructures will actually increase the sensitivity of a sensor. Okay. Now let's come to the problem 2. Which of the following parameter does not affect the deposition rate of CVD process? Is it precursor and their partial pressure, length of the susceptor, and activation energy of the precursor, or rate of carrier gas flow? Anyone? Okay. So if we remember how a CVD looked like, okay, how a CVD looks like. Uh, in gen in general, we have a coarse tube and will be closed from both the sides, and gas will flow in and out, in and out of it. Okay, and here we put the susceptor. Then there will be heat, like heating of this tube at different temperatures according to our need. So partial pressure, partial pressure of the precursors, like precursors can be put here or here according to whatever is their activation energy. Okay, this will have effect on the partial pressure of the precursor will have effect on the final deposition, because how much amount it is and how well it is how well it is flowing and how it is deposited, that will have an effect on the deposition rate of the CVD process. Activation energy of the precursors is important because we must reach the activation by heating or either by uh, presence of some you say catalyst. We must reach the activation energy of the precursor. So this is a critical parameter, and that is why this is also important. Rate of carrier gas flow. Yes, this is also important because uh, how much we are flowing. If we are flowing very less, so it might happen that the material does not move to like the transport does not occur, it does not move to the sample. And if it is very high, it might happen that it moves, but it moves so fast that it was not able to deposit. So this will have effect, this will have effect, this will have effect. But the length of the susceptor does not have effect because it is not the length, but it is the position where you are putting the sample and the uh, precursor. It is not the length of the susceptor. Okay, so uh, this is the thing that will not have effect on the deposition rate of the CVD process. So the correct answer for this will be the length of the susceptor. Okay, now let's come to the next question. At lower pressure, an increase in mass transfer coefficient during LPCVD, LPCVD means low pressure CVD process, will change the mode of operation. What will be the process change? Okay. So it is saying that when we have a low pressure CVD, that means we have the CVD1 in which we are doing the deposition at low pressure. Okay. So it is at low pressure. That means the pressure has been reduced by using a vacuum pump or a normal pump. Okay. So that means there are no other contaminants and no other things. Okay. An increase in mass transfer coefficient during LPCD will change the mode of operation. Okay. How will the process change? The system operation switches to mass transport limited regime, or the system operation switches to the surface reaction control regime. The system operation switches to the diffusion limited regime. Okay, so remember that there were different regimes like mass transport limited regime, surface reaction control regime, and diffusion limited regime. Okay, so how will the process change? Okay, how will the process change in this case? So as the mass transfer coefficient is increasing, okay, so more more amount of uh, precursor is available, and that is why it will be mostly mass transport limited regime. That means that sorry, I'm saying it wrong. That as the mass transfer coefficient increases, so it will be like, as we know, the critical part, that is the one that is slowing the reaction, like the that part where some in a equation in a set of chemical reactions also, the slowest reaction is the rate determining reaction. Okay, so here there is a if there is a limitation of the amount, like how much mass is reaching to the reaction point or reaction junction, that is limited. That is why it will be a mass transport limited region. Whereas since there is no like sur surface reaction is already happening and there is no extra mass there, so that so it will be fine. Like surface reaction will go at its normal pace, and diffusion will also occur fine. But the problem here will be that how much mass is transported there, and that is why this reaction will switch to mass transported mass transport limited regime. Which of the following is are true for dry etching? Okay, remember we talked about dry and wet etching in the previous week also. So it is saying that can be done only in a single wafer at a time. Okay. Difficult to fabricate sacrificial layers in MEMS-based devices. It is saying true for the dry etching. So difficult to fabricate sacrificial layer. Highly anisotropic, all of the above, or none of the above. Anyone? Yes. So none of the above is true for dry etching. Why? Because we can have multiple wafer at a time, and we we can even create sacrificial layers in MEMS-based devices using dry etching. In fact, it is showing as it is said it is highly anisotropic, but in fact, dry etching can also be isotropic and highly isotropic also. Remember, we talked about HF6, HF6 dry etching, so that was highly isotropic. Okay, so none of the above is true for dry etching. Which process is used to produce high purity, high performance solid material? Is it CVD? Is it PVD? Evaporative vapor deposition or molecular vapor deposition? It's high purity, high performance solid material. And mostly when we are talking about these deposition techniques, we are talking about the functionalization materials. Okay. So one, chemical vapor deposition, right? That is, why chemical vapor deposition? Why not PVD or why not evaporative vapor deposition? Because here, actually, there is no term like evaporative vapor deposition. It will be uh, thermal evaporation, and that also actually comes under PVD only. Okay. So in all these cases, the material is already prepared. The solid material is already available to us. We are just changing its form. In PVD, we are just either evaporating it or we are uh, sputtering it, like we are taking some molecules at once and then depositing it somewhere. So we are not preparing the solid material. But in case of CVD, with chemical reactions, we are preparing the solid material. In case of CVD, using the precursor and the gas flow, we are actually uh, facilitating the chemical reaction that will happen there. And as such, we can produce high purity and high performance solid material from CVD. In case of PVD or thermal evaporation, also we can deposit high purity and high performance solid material, but in that case, we should have a high quality, high purity material available with us, high purity solid material available with us. But in case of CVD, we can produce that. Okay. Volatile organic compound. Remember it from the first week also. We talked about volatile organic compounds are formed from their respective liquids easily. So we discussed that time also that these are such compounds which are in liquid phase, but at room temperature itself they can easily convert to gas phase and they can evaporate. Okay, liquid easily because of low diffusibility at room temperature, low vapor pressure at room temperature, high vapor pressure at room temperature, or high sublimation temperature. Okay, so let's take one by one. Okay. Low diffusibility at room temperature. So that means it is not easily diffusible at room temperature. If it was so, it will not actually move from one place to another in the environment. So this should be wrong. We'll see. According to me, it should be wrong. Okay. Low vapor pressure at room temperature. So it is like it has low vapor pressure, and that means it is very stable at room temperature. If it was so, it will remain in its state. Okay. So this should also be wrong. High vapor pressure at room temperature. So if it has high vapor pressure, it will be unstable. The surface will be unstable and it will try to change its phase. And high sublimation temperature. Sublimation, in this case, sublimation occurs from solid to gas, right? Directly. So here we are talking about liquid. Okay. So it should not be this. So I think it should be C. Yes. So high vapor pressure at room temperature. And due to this high vapor pressure, the surface is unstable and the molecules easily tend to move in the outer environment, and they are not actually evaporating, they are just diffusing in the environment. It is a bit different from uh, this. It is a bit different from the evaporation, in which case we need to heat it. Okay, so here it is already in a bit unstable state. The surface is at unstable state, and so the surface molecules move, and one by one, different layers move out. Okay, which of the following are different types of CVD? Atmospheric pressure CVD, like I talked, low pressure CVD. In fact, we have discussed this also. Plasma enhanced CVD, or all of the above. So all of these are types of CVD. Atmospheric pressure CVD is in which we just do these reactions at atmospheric pressure. We are not creating any low or high pressure. Low pressure CVD is in which we decrease the pressure and the decrease the pressure. That means we remove the external like available gas from it, and then we only flow the desired gas. This will have the effect that it will increase the mean free path. Remember, we have talked about mean free path very frequently. Okay? So this is possible. Then plasma enhanced CVD, in which case a plasma is used in conjunction with, it is mostly also low pressure CVD only with, but with plasma. So RF plasma or DC plasma to assist the process that is already happening. Okay. Which of the following statement is true for AP-CVD? AP means atmospheric pressure CVD. Low sticking coefficient of deposited material gives better step coverage, high deposition rate, widely used for silicon deposition, or all of these. Okay. Low sticking coefficient of deposited material means here the deposited material is not very easily sticking on the sample, and that is why it gives better step coverage. Okay, the rate is very high because there is no constraint put, normal reaction occurs. Okay, so rate is high, and it is, yes, it is very frequently used for silicon deposition. Like we have silicon wafer, but sometimes we even need to deposit some silicon, and in this case the silicon will not be having any orientation. When it is being deposited, it will be mostly amorphous amorphous silicon, and what we are using in wafer, it is crystalline. Okay, so it is used in silicon deposition, but remember that it will not have this 100 or 111. It will have for a small area, but overall it will be amorphous in nature, like different crystal planes. So it generally tries to orient itself, but overall, if we look, it will not have one single orientation. Okay. Rate of deposition of chemical vapor deposition technique depends on gas phase diffusion of the precursor, rate of reaction, temperature, or all of this. And in case of CVD, how so gas phase diffusion of the, so how well the precursor is diffusing in the gas phase, how well it has diffusibility, that is one factor. Rate of reaction certainly is a factor, since we are talking about chemical reactions. So if the rate of reaction is high, we will get more deposition. If the rate of reaction is less, we will get lesser lesser deposition. And temperature plays an important role, since it is used to activate the precursors, as well as we have seen that most of the chemical reactions have some optimal value at optimal temperature at which the reaction is the fastest. Okay, so all of these are the factors that determine the rate of deposition of the chemical vapor deposition technique. Fine. In low temperature regime of CVD, the rate of reaction does not vary significantly with temperature, is very sensitive to temperature, is very sensitive to molecular weight of the precursors, at surface of the substrate, does not depend on the crystal orientation. Which of the following is true? Okay, so it is saying that low temperature regime of CVD. That means the tube, as discussed, is not heated equally. So the CVD, the deposition actually occurs at different different kind of deposition occurs at different positions. So suppose that this is heated to some temperature, say 800, then this one was actually 200, or this one was also 500, but this one was at lower temperature. Okay, this one is 200 maybe. It will not remain like that. It will actually go up to 300 or something due to the heat. So it says that it does not vary significantly with temperature. It's very sensitive to temperature, is sensitive to molecular weight of the precursor. This will have an effect, but this will have an effect on the rate of reaction. Okay. At surface of the substrate does not depend on crystal orientation. It depends on the crystal orientation because, as I said, that they try to orient themselves according to the crystal. What is the orientation of the crystal? That is a general tendency of the uh, molecules that they try to orient themselves. Otherwise, some stress develops, and that is automatically handled. Okay, that like relaxes and all, and that is why this is also not true. This is not true. Okay, and since this here the temperature is low, any change in the temperature will have significant effect on the rate of the reaction, as the rate of the reaction will the rate of the reaction is highly dependent on the temperature. Okay, so it is very sensitive to temperature. Okay, now let's come to the next question. The silicon wafer is doped by diffusion of boron to a depth of 200 nanometer to define the active device area. Okay, so let's first draw it. We have a silicon wafer. Okay, is doped by diffusion of boron to a depth of 200 nanometers. So let's say that this part is already doped with boron. Doped with boron means it will become a bit n-type. Okay, and this depth is 200 nanometers. The next process requires deposition of the silicon dioxide layer as an insulating layer. Okay, so now we want, say, now we want that on top of it we deposit silicon dioxide. Which technique can be used so that the deposition profile will remain unaltered? That means this area, this doped area is not disturbed, and we get the deposition of SiO2. Any idea? Okay. So the problem with this, the problem in this that can occur is that if this is being done at a higher temperature, okay, so this boron will try to diffuse in, or like it will have some changes. So if we don't want, because the uh, whole silicon is not doped with diffusion, some part of it, and that also very thin layer at the top is only doped. So we don't want its profile to change. So this thing has to occur at a bit lower temperature. APCVD and LPCVD, they rely mostly on the activation due to temperature. But in case of plasma enhanced CVD, what happens is that there is some temperature, but along with that, it is mostly due to the plasma, which is cold. Okay, the reaction rate is increased or enhanced by using plasma. Okay, so at lower temperature also the deposition can occur, the chemical reaction can occur, and that is why this is the one that will be the preferred one in this case. Fine. Okay. Suppose I need to grow. Oh, sorry, here I should put some name. Uh, Suppose I need to grow or deposit 111 oriented silicon. So we need 111 then silicon epitaxy. Uh, my options for the growth are APCVD, PECVD, or LPCVD. So it is like we want the orientation and that also epitaxy to be grown epitaxially. Okay. Whenever we are talking about epitaxy, we mostly talk about MOCVD. That is the best option. MOCVD is the best option to do epitaxial growth. But here MOCVD is not the option here. Okay. So if we have to orient that, then the best option will be APCVD or LPCVD. Why? Because at higher activation temperature, the molecules try to orient themselves with the underlying crystal structure. Like if this is the it, so if like if a silicon arrives here, it will, due to its energy, it will have adequate energy to try to orient here, like shift itself here, right? And so the crystal growth will take place. Whereas in case of PECVD, since we don't have the temperature, uh, the reaction will occur, silicon will be produced, but it will not try to, uh, it will not have adequate energy to orient itself. Okay, and that is why APCVD or LPCVD can be used to deposit, but in that case, the lower underlying substrate must also be 111. Then only it will try to orient itself. Okay. When depositing silicon dioxide using LPCVD, high temperatures are needed to achieve non-conformal deposition. Is it true or false? LPCVD means low pressure CVD, and we are trying to achieve non-conformal deposition. So if we are trying for non-conformal deposition, we can go for normal temperature. Higher temperatures are not needed. Okay. PCVD is useful for deposition when low melting temperature films are already present on the wafer. Okay. So, like I discussed earlier also, when we already have something that has that can have effect on the of temperature on this, very low deposition rates are required. No, it is not like that because plasma enhanced CVD will not have low deposition rate. In fact, we are using the plasma to increase the deposition rate, right? There is no thermal budget available for the doping profile. That means, like we saw in the case of boron doped silicon, that we cannot go for higher temperature. Like if we go for that, the doping profile will change. And LPCVD is not available due to contamination restrictions of the available tool. Okay, so this is also an option since in case of LPCVD, there can be more contamination compared to PCVD. Okay, so these are the reasons, but this will low deposition rates are required. Like this is not the reason because anyway that is more dependent on the you can control the deposition rate not by using PECVD, but by changing the temperature in case of LPCVD and EPCVD, as well as the flow of the gas and the precursor amount, and these things can be changed if we want low deposition rates. Okay. Is it possible for ions to enhance its rate significantly when they act in conjunction with free radical? So it is saying that there are ions, say free radicals are being used in dry etching process. Okay, and there are ions process. We are introducing some ions. Will it increase the H rate? Since ions are highly energized, and it will affect the plasma, and it will certainly increase the H rate. So it is true. Which type of etching process is used in this figure? Okay. So the first one, a slanted structure is formed. Okay. Though the mask is still here only. So ideally it should have been formed till here. That is what we ideally think. But here, this structure, remember we discussed about this in the previous week many times, that a plane can also work as H stop plane. Okay. So here, when the etching occurs, it is being stopped by this plane. Okay. 111, 110, or like it will depend on the material as well as the etching. Okay. The second one is we have the mask still here. So the ideal case was if it was to be done anisotropically, it should have been like this. But in this case, the material went in and it etched in all the directions. Okay, as if like it started from here and then it grew like this, like this, like this. It kept on increasing the profile. So what kind of etching processes are used in this? First, certainly both of these will be occurring in case of wet etching only. Okay, and this one is an anisotropic process. Why anisotropic? Because the anisotropy is being determined by the uh, plane in the substrate, but it is anisotropic process since it will not be equal in all the directions. But in this case, since it is equal in all the direction, it is not depending on the plane, it is not depending on any other factor, it is just going equally in all directions, so it should be isotropic. Always remember, iso means equal or uniform. Okay, isotropic. So wherever we have an isotropic, yes, yeah, B should be the correct answer. Okay, yes. Now let's come to some questions related to lithography. Again, why hard bake is required? To reduce the solvent content in order to stabilize a resist film, making more resistant to wet chemical etching, reduce the undercut of the resist during wet chemical etching, both B and C. Yes. Okay. So remember the process of lithography. What it was? First we on the wafer, first we do the spin coating of the PR, then we do a soft bake, and then we do align and expose, then we develop, and then we do a hard bake. Okay. So by this time, in fact, by this time itself, it is dried and a bit in solid structure. It is not in liquid form or like there is no solvent in it. That we have taken care in this step only. Then we are aligning, exposing, developing. So we have the mask or the pattern ready. Now, why we do hard bake? There are two reasons to do hard bake. First one is that it will become more resistant to chemical. Like after this, we will go for uh, wet etching or dry etching or whatever processes are to be followed. So we don't want that in that process our mask actually peels off, or like our mask itself gets etched. That is not our purpose. Okay. So one is to make it more resistant to wet chemical etching. The second one is to reduce the undercut. That is like if it is like this, it should not after like subsequent process it does not become like this, or the structure at the bottom does not become like this. This we want to reduce because here it does not add, so it solidifies, it hardens. It is that is why it is called hard bake also. It hardens. It will be very difficult to be etched by during the wet chemical etching. So B and C both should be correct. Now this should also be correct. This is both B and C. Okay. Now why soft bake is required? So as I discussed earlier, like when we are doing the spin coat, after that process also, though we have dried like it is spinning at a very high speed, and so and it creates a very thin film, but that film is still a liquid. Okay. So we keep on spinning for some more time so that it solidifies. But sometimes some small amount of liquid still remains, and so a soft bake is done so that it just solidifies and it stabilizes. Like there should be nothing like if we do it like this, it just flows. It should not be like that. Though it will not flow directly, but yes, there will be some internal flow, like very slow, and that can be difficult to develop, or in fact during exposure it will not have a uniform exposure, since uh, the exposure dose, how much energy is to be given for it to be able to dissolve, or in case of positive resist, and not dissolve in case of negative resist. So that actually depends on the thickness. So if we are using one, that will have difficulties, because if somewhere it is thick, somewhere it is thin, that can have problem. So to reduce the solvent content in order to stabilize resist. Okay. Next is, which techniques involves selective removal of substrate to produce mechanical components? Is it surface micromachining, bulk micromachining, both of these, or all of the above, or none of the above? The substrate is selectively being removed to produce mechanical components. So this is called bulk micromachining. Mechanical components, when we are talking about, that means which can move, or which can create some movement, like gear, gear kind of structure, pulleys, cantilever, and such structures. So there actually the uh, thickness of the structure, thickness or the depth in the structure will be very high. Okay, and in this case it comes under bulk micromachining, whereas surface micromachining is in which we are working things on the surface. So mostly when we are making electronic devices, like transistors and this, or we are depositing electrodes, then we are patterning, that comes under surface micromachining. So bulk is when we try to etch deep. Okay. What do you mean by high aspect ratio etching? High aspect ratio. Like when we talk about aspect ratio, the first thing that comes to mind is the laptop or TVs or mobile phones aspect ratio. That is, like if this is the whole screen, like so, mm, mm, if this is the screen, I will not go till the corner. It just senses some gestures. Yes. So this is the whole screen. So what is the aspect ratio? That is this side ratio with this side. So length is to breadth. Okay. So when we are talking about high aspect ratio, that means one dimension will be very small compared to the other dimension. Like the length can, if a structure like this is there, a screen like this structure comes. So this we can call it high aspect ratio, high aspect ratio screen. Whereas if we have something like square, this is low aspect ratio. But why? Because it will have a aspect ratio of 1:1. Both sides are equal. So it is an alternate term used for through-hole etching. It is not necessary, okay, for through-hole etching, because uh, when we are talking about high aspect ratio, it can have structures like this on the top. Okay, I will show you some. Yeah, like such a structure. It is not going to till the end, but this structure you see, this is a pillar kind of structure or a standing wall kind of structure like this. You see, this is a very perfect high aspect ratio one. Okay, so the opening of the etching area is large, uh, not very necessary. Okay, that opening is large. The degree of anisotropy of the etch profile is very high. Yes, because it is very anisotropic. You see, when the etching is has happened, it has happened in one direction, almost negligible in this direction. Okay, and this also, you see, most of the etching is in this direction and not in the sides. In this case also, you see, it is not perfectly a rectangular profile. It has tapered inside, but still it is very anisotropic, not one but very much. Okay, so the degree of anisotropy of this the H profile is high. Okay, and that is called as high aspect ratio etching. Okay. Which of the following holds true for chemical wet etching of silicon wafer? Okay, etch rate is etch rate in isotropic wet etching does not depend on crystallography orientation. Etch rate in anisotropic wet etching depends on crystallographic orientation. Bulk and surface micromission can be performed. Remember, isotropic, that means equal in all the direction. So there is nothing, no crystallographic orientation dependence. So does not depend. So I think this is correct. H rate is in anisotropic wet etching depends on crystallographic orientation. Yes, we saw that some planes are used as etch stop for this anisotropic wet etching, wet, wet etching. So this is also true. Bulk and surface micromachining can be performed. So we have seen at many places that we were doing surface etching, like doing the electrodes, and then ID pattern heaters, they were surface micromachining. Whereas when we want to create high aspect ratio things, cantilevers, or maybe like a diaphragm like structure, like suppose we want to make the pressure sensor here, we will put the electrodes, everything, but from the bottom we will etch it like this. Okay, so that when some pressure occurs here, this whole structure moves, like there will be some bending on it, and that bending can also be very easily detected on the this on the surface electrodes, because their shape will change. And remember, the resistance depends on L and B and such structures. So the top structures, they are made using surface micromachining here. It is not always necessary that the top will be surface and bottom will be bulk, but here it is surface micromachining. And at the bottom, it is made by using bulk micromachining. Okay? Because this is like going through almost this whole thickness of the wafer, that is say around 350 micron. Okay, so say we remove all 320 or 300 microns or 310, 320 microns, and then a very thin diaphragm of uh, 20, 30 microns is made, and that acts as a pressure sensor, because it will be such a thin layer will actually be sensitive to the pressure, like there will be some bending, and that can be detected. So all these are true in for the wet chemical wet etching of the silicon wafer. Okay. In plasma etching, okay, sorry, I missed to put the question here. Directly the answer is there. In plasma etching, the chemical etch due to free radicals is highly anisotropic in nature. So when we are doing plasma etching using free radicals, that is DRIE or RIE also, it is fine. Okay, it is highly anisotropic in nature. No, it is not. It is highly isotropic. It is not selective, right? It is like we discussed. Uh, it is very fast, very accurate, but it is not selective. Okay, in whatever direction it will go, it will just do etching, isotropic etching. That is why this is false. So that's all. Any questions you are free to ask. That's all for today. Thank you all. See you all in the next class. Thank you.